Good morning to respected Somojit sir and my fellow batchmates. I, Dattatreya Saha, and my friends Shriya, Sahana and Debolina Biswas are going to present the topic Harnessing Machine Learning for Development in Prediction of Weather Forecasting and Climate Modeling. We are going to present this topic. The contents in this presentation are Introduction, Natural Disaster Management, Weather Forecasting, Climate Modeling, Motivation, Problem Representation and Solution, what is Machine Learning, Traditional Methods versus Machine Learning, Mechanism, Machine Learning Concepts and Algorithms, Application, Case Study and Examples, Reference, Acknowledgement. What is Natural Disaster Management? Natural disasters like hurricanes, floods, and droughts have devastating impacts on communities worldwide. Accurate prediction of weather conditions and climate changes can significantly improve disaster preparedness, minimizing loss of life and property damage. Natural disasters like hurricanes, floods, and wildfires have profound and devastating impacts on communities worldwide. Accurate prediction of weather conditions and climate changes is pivotal in disaster response, as it can significantly reduce the loss of life and property damage. Natural disaster management involves predicting and mitigating the impacts of these unpredictable events, encompassing a range of strategies and tools. Machine learning stands out as a formidable ally in this endeavor, as it excels in processing vast amounts of data from diverse sources such as satellite imagery, weather stations, and ocean buoys. Machine learning algorithms are adept at discerning complex patterns and trends that might elude human analysts, thereby contributing to more precise forecasts. One of the paramount challenges in natural disaster management lies in anticipating and mitigating the impacts of events like hurricanes, floods, and wildfires. Machine learning emerges as a potent tool in this domain, offering substantial advancements in weather forecasting and climate modeling. Through the meticulous analysis of massive datasets, machine learning algorithms identify intricate patterns, subtle deviations from historical norms, and potential triggers for natural disasters. This data-driven approach enhances prediction accuracy, allowing authorities and communities to better prepare for and respond to this crisis. The integration of machine learning into natural disaster management marks a critical step forward in building resilience and safeguarding lives and property in the face of the unpredictable forces of nature. Now, let's get an idea of what is weather forecasting. Weather forecasting is the use of science and technology to forecast atmospheric conditions for a certain place and period. Meteorologists gather data from various sources including satellites, weather systems, buoys, and radar systems. This data is fed into computer models that simulate the behavior of the atmosphere, allowing meteorologists to make predictions about future weather patterns. Running numerical weather predictions models require powerful supercomputers due to the complex calculations involved. These supercomputers can process massive amounts of data and perform calculations in real time, enabling timely weather forecasts. What is climate modeling? Climate model involves using complex models to simulate and predict long-term patterns of temperature, precipitation, wind, and other climate-related factors. These models help scientists understand how human activities and natural processes affect the Earth's climate, including the impacts of greenhouse gas emissions and other environmental factors, for instance, global warming. And climate models provide insights for policymakers, allowing them to assess potential scenarios, plan for adaptation strategies, and make informed decisions to address climate change. So the application of machine learning in climate modeling can be explained. Data-driven insights. Machine learning leverages large climate datasets to automatically identify and analyze complex climate patterns such as El Nino and La Nina. It can discern subtle changes and relationships that might be challenging for traditional statistical methods. Early warning systems. Machine learning models can forecast the onset of climate phenomena like El Nino with greater accuracy and lead time. This information is crucial for predicting the resulting weather anomalies and potential natural disasters. Global weather impact. By recognizing climate patterns and their interactions, machine learning helps researchers understand their influence on global weather systems. This knowledge aids in predicting and mitigating the effects of extreme weather events such as hurricanes, droughts, floods. Climate change analysis. Machine learning also plays a crucial role in tracking long-term climate change trends. It helps scientists analyze historical data to identify shifts in temperature, precipitation, according to our understanding of climate change's causes and impacts. Hence, the motivation for choosing this topic lies in the potential to save lives and minimize damage on a global scale, and hence reduce the economic and environmental impacts of natural disasters. By improving weather forecasting and climate modeling using machine learning, we can provide timely warnings to people in affected regions, allowing them to take precautionary measures. So, machine learning can be effectively used to enhance our ability to predict and manage natural disasters. This technology-driven approach improves global disaster alertness, safeguarding lives and property. Now, I would like to call Debolina to continue the presentation further.
So now the problem representation. Hence, the problem of natural disaster management is a critical global challenge with the potential to cause significant loss of life and property. Natural disasters encompass a wide range of events, including hurricane, tornado, floods, wildfires, earthquakes, and much more. The challenge lies in predicting when and where these disasters will occur or take place. Traditional methods for weather forecasting and climate modeling rely on complex situations and historical data analysis, which can be computationally intensive and not always precise. The most vulnerable groups get the direct impacts of these disasters. Now the problem solution. An effort made to minimize disasters can be provided by the use of machine learning in the areas of disaster management, which consists of data source along with models and algorithms used. Accurate predictions of weather conditions and climate changes can significantly improve disaster preparedness and responses. Machine learning can significantly improve by leveraging vast data sets of meteorological and environmental information along with advanced algorithms to make predictions with greater accuracy and speed. Machine learning algorithms can identify complex patterns that humans might miss, which leads to better results. What is machine learning? Machine learning is a subset of artificial intelligence that focuses on the development of algorithms and statistical models that enables computers to improve their performance on a specific task through learning experience without being explicitly programmed to do so. In essence, it's a way for computers to learn from data and make prediction or decisions based on that learning. Then it allows software applications to do so and imitate intelligent human behavior. Machine learning can identify patterns and correlations that humans might miss. By integrating machine learning into weather forecasting and climate modeling, We can harness its data processing and pattern recognition abilities to make much more accurate predictions, ultimately contributing to improved disaster management and climate understanding. Now, the difference between traditional methods and machine learning. In traditional methods, these models are based on the laws of physics, fluids, thermodynamics. They use the differential equations to simulate the behavior of the earth. Machine learning models do not explicitly encode the underlying principles. Instead, they learn patterns and relationships from data which we have applied. Traditional methods require deep understanding of physical processes and extensive data assimilation, including measurements from various sensors, satellites, and weather stations, whereas machine learning models can work with a wide range of data types, including historical climate records and even unstructured data like satellite images. Machine learning models excel at handling large data sets and can discover non-obvious relationships with that data. Traditional methods are less flexible in adapting to rapidly changing conditions or incorporating new data sources without significant modifications, whereas machine learning models can adapt more easily to changing circumstances. They can be retrained with new data to improve accuracy and evolving weather patterns. Now I would like to call Shriya Sahana to continue the further presentation.
So, as my friends now discussed, that machine learning can be useful to predict weather data very accurately. What are the exact machine learning concepts and algorithms that can be used to do so? Machine learning algorithms use historical weather and climate data to learn patterns and relationships. Then they apply this learning to new data to make predictions. For example, algorithms like neural networks and decision-making trees can recognize complex patterns in temperature, humidity, wind patterns, ocean currents to forecast weather and climate changes. In weather forecasting and climate modeling, machine learning algorithms analyze patterns in the atmospheric and oceanic data to identify correlations and relationships that contribute to weather and climate changes. For instances, the recurrent neural networks (RNNs) can capture temporal dependencies in weather data, making them suitable for time series predictions. So, we have mentioned here a few points in weather forecasting and climate modeling and the various algorithms that can be employed in this process. For instance, regression models. Simply speaking, linear regression and polynomial regression is used in this practice. The purpose of using it is linear regression is used to model the relationships between dependent variable, in the case temperature, and one or more independent variable, time. It identifies and is suitable for identifying simple linear trends in data. Hence the application. So you can say that the linear regression is used to predict temperatures over time, hence assuming a linear relationship between the time and the temperature. So polynomial regression is an extension of linear regression that allows for modeling more complex relationships between variables. It can capture non-linear trends in the data, as well as in the context of temperature prediction. We can use polynomial regression when temperature in fluctuations don't follow a straight line but have a curvilinear pattern. Time series analysis. ARIMA models are specifically designed for analyzing and forecasting time-dependent data, such as temperature trends over years. ARIMA stands for Autoregressive Integrated Moving Average, and it combines autoregressive and moving average components to model train series data. ARIMA can help you to understand and predict long terms of temperature trends, seasonal variations, and short-term fluctuations. Decision trees and random forests. Decision trees. The purpose of using this decision trees and random forests are used to model complex relationships between multiple factors, example humidity, wind speed, precipitation, and temperature. They can handle non-linear relationships and interact between climate factors. We can use these decision trees to predict the temperature based on a combination of meteorological variables. Random forests in particular are effective at reducing overfitting and improving prediction accuracies by aggregating multiple decision trees. Neural networks, including CNNs. Neural networks, including deep learning models like convolution neural networks, are designed to capture complex weather patterns and relationships in data. In climate science, CNNs can process satellite images and extract features like cloud cover, sea surface temperature, and more. CNNs can also be applied to image-based climate data analysis, such as identifying, tracking cloud patterns, or monitoring changes in sea surface temperature of satellite imagery. Support vector machines. SVMs are used for classification and regression tasks. In climate science, SVMs can classify climate changes and patterns like El Nino, La Nina events and make effective data storage and historical data predictions based on these historical data perceptions. These SVMs are effective at identifying and predicting significant climate change that have broad impact on regional and global weather patterns. Assemble models. Boosting and bagging. Purpose of assemble models combine multiple models to improve prediction accuracy. Bagging, bootstrap, and aggregating and boosting are two popular assemble techniques. These methods can be applied to any of the above decision trees, linear regression, or to create more robust and accurate climate predictions by leveraging the strength of multiple models while mitigating their weaknesses. Often a combination of all of these methods is used to gain a comprehensive understanding of climate phenomena and make more accurate predictions. So, creating a real-time weather and climate prediction model is complex and a resource-intensive task that typically involves collaboration of meteorologists, data scientists, and access to vast data sets and computational resources. Data collection, data pre-processing, feature engineering, model selection, model training, model evaluation, real-time data integration, model deployment, model monitoring and maintenance, collaboration with meteorologists. These are the ways to apply and incorporate in creating such a model which can be used for prediction. Please note that this is a very simplified outline, and the actual implementation would require significant expertise, resources, and domain knowledge on this regard. Case studies and examples. IBM's Deep Thunder is a high-resolution weather forecasting system and service that was developed by IBM in 1996. Combines advanced weather modeling and data analytics with high-performance computing to provide detailed and accurate weather forecasts. Deep Thunder is designed to help organizations and businesses make better decisions related to weather-related risks and opportunities. NOAA stands for National Oceanic and Atmospheric Administration. It is a United Nations States federal agency that is in the Department of Commerce. NOAA is responsible for monitoring and forecasting weather, oceanographic and atmospheric conditions, as well as managing and conserving the nation's coastline and marine resources. All these models use complex AI and ML algorithms to compute data.
All beings on this planet are affected by atmospheric phenomena we call the weather. Weather systems determine when and where to produce our food, how our infrastructure must be built to be resilient, or when to prepare for different climate hazards. Because of this, humans have invented all sorts of measuring tools to understand future climate conditions, which, lucky for us, means we have loads of data from observations. All of this data, of course, has been on quite a technology journey. From being collected on paper, to being uploaded on local servers in basements, to being moved to open platforms that normalize all the different data formats from sensors into cloud servers. This has been thanks to the labor of love of so many that know how valuable it is to get this information into as many hands to find more solutions faster. It's also been incredibly challenging to compute weather models. Historically, these have been physics-based. This means that many combinations are calculated in order to simulate natural forces. This requires loads of expensive and time-consuming computer resources. And by the time calculations are finished, it's common for weather patterns to have changed. Up until recently, this has been changing by building predictive models with a radically different approach using an AI technique that uses neural networks called deep learning. In this case, we use satellite images that have labels of phenomena to train a model to make weather predictions. Unlike traditional physics simulations, we do not need to feed it a sequence of complex rules to calculate many weather forces. Instead, neural networks are not so literal. They take a step back and find visual patterns of cloud behavior from satellite images based on past examples. This is similar to how we process information with our eyes. Here's a quick example. Assume we analyze two planets. They both have gravitational pulls that affect each other. Now add more planets to the system, there's additional gravitational interactions to now account for. Calculating the forces between all of them grows into exponential combinations. On the other hand, training a model using neural networks by observing the behavior of different initial states from a variety of planetary systems, along with what happens as the next step, it eventually helps make predictions without having to calculate all the forces. What's even more exciting is that such a model can be shared with others to generate forecasts that are nearly instantaneous. Furthermore, pairing this technique with a powerful data processing hardware like GPUs and TPUs helps users get more accurate predictions at a fraction of the cost and time from standard physics simulations. Their model is called MetNet. It performs precipitation forecasts that we see in the evening news at an amazing high spatial resolution of 1 kilometer, within a time resolution of 2 minutes. It outperforms other traditional models that forecast up to 7 to 8 hours. This can help to predict extreme weather, especially as we experience further climate changes. More specifically, it can help forecast severe rainfall in a local region within a relatively short period.
Thinking about this problem, I think we had two goals in mind. One is that we want to capture the dynamics, but in addition, we didn't want to create any very expensive or complicated physics, and so we wanted to pursue a physics-free approach. That is, we want to predict the weather purely by example. We can take examples that have been collected from satellites and radar stations over the last few years and use those as examples to train a neural network to make predictions about the future. Google has been an excellent place to pursue this work for many reasons. One of them is that we have scalable cloud platforms that make it possible to develop very large-scale models and study them on large-scale problems. The other reason is that when we study the Earth, the data sets that we work with are large. The Earth is large, and if we want to understand the Earth at very high resolution, these are very large data sets, and they're really out of reach of a person who might want to download those data sets and use them to study weather forecasting at home. In contrast, at Google, using our cloud platforms, we can download these large data sets and make them available to everybody, anybody who wants to study this work. And so what we found is that the results of our research are useful not only to make scientific impact, but to make this technology accessible to anyone who has the desire to study it.
In honor of this awesome data analytics problem, let's see how to approach it via an architecture diagram. We will use Google Earth Engine's data sources and Google Cloud's computing resources. For this US-based sample, we'll use 3 datasets from the Google Earth Engine catalog. The first dataset is GOES-16 from NOAA, which stands for the National Oceanic Atmospheric Association. It collects information every 30 minutes, which is great for real-time monitoring for weather or wildfires, for example. This is possible because the GOES system uses satellites stationed above the equator and are synced to match the Earth's orbit, so it's only available in the Americas. Each picture has a resolution of 2,000 meters per pixel. We'll talk about this later. The second dataset is the Global Precipitation Measurement, or GPM, by NASA. It includes the amount of precipitation measured in millimeters per hour. It has a resolution of about 10,000 meters per pixel. And the third dataset is Global Elevation. Next, we ask ourselves what our input data and output labels are. For inputs, we'll use data from GOES, GPM, along with elevation. For outputs, which is how we label our predictions, we'll use GPM's precipitation labels to predict the future. We pair inputs with their respective labels together into a training example. These are where our model will learn from. After identifying our inputs and outputs, let's export our training examples into a training dataset by using a data flow pipeline in Google Cloud. Dataflow is a data processing service that helps speed up the export process from hours to minutes using the Earth Engine's high volume endpoint. We typically use stratified sample to gather a balanced amount of points per classification, but because we are working with regression, we have to bucket our labels into classification types. We do this by turning all our numeric labels into integers, so they all fall into a bucket. We chose 31 buckets that represent 0 to 30 millimeters of precipitation per hour. And then, for example, if we choose 100 points for each classification bucket, and then grab 1,000 random dates, we end up with around 3 million training examples. Note we choose to make 2 predictions, one at 2 and 6 hours in the future, but you can make as many as desired. And in terms of the amount of inputs needed, the more past data, the better. But we have found that at least 3 input points are needed to give enough context to make any predictions in the future. In our case, we chose to feed our model with data from the current time and at 2 and 4 hours in the past. Since we are using PyTorch, an ML library, we save each training example into a compressed NumPy file format into cloud storage. Next, we write a script to train the model. First, it splits our dataset 90-10. 90% used for training the model and 10% used for testing the model's accuracy on data it has never seen before. Then we define our model, but there are some things to consider. Satellite sensors can give very large numbers, but our model prefers smaller numbers. So we create a normalization layer from the training dataset, which gets your raw inputs and normalizes them into smaller values. Then we pass the normalized inputs through a 2D convolutional network. For simplicity, we only use a 2D convolutional layer followed by a 2D deconvolutional layer. Each layer is connected by a ReLU layer since it's a good general purpose activation function. Next, we need to know what our goal is. In this case, it's regression. If you are new to machine learning, typically for regression, we use a linear activation function. But here we can't have negative precipitation. Because of this, we can use ReLU instead because it replaces negative values with 0. So we end up with only non-negative values. Finally, we train the model in Vertex AI and save the trained model in the PyTorch model file format into cloud storage. We can eventually host it into Cloud Run, which is a web hosting service. And finally, in order to visualize our predictions as a map, we can use a notebook like Colab, or we can bring it back into Earth Engine.
So now I'm going to use Google's open source code, which has been used to predict weather forecasting models. It uses real-time data in the code, which can be used to predict data in future. The screen visible. This is a very complex code to understand, to be honest, but in simple words, if you can see in the screen where I'm pointing my cursor right now, the data has been input, we have given data values in the input. The date and time of a particular zone has been mentioned. The points, the longitude and the latitude have been clearly mentioned over here. It is being given as an input. The path size has also been mentioned here. So these are simple inputs that has been given to train the model. Slowly, the input data which has been shown here, these images are all the inputs which the model is being shown to train. Now we are training our AI model, like machine learning and AI model, to simply identify and recognize these patterns and then predict a model so that which can help us to predict the climate changes of the particular area in future. As you can see, this is not a very clear image because just a small amount of data has been given to it. Slowly it recognizes these patterns and gives us a clearer image, which in the end shows like this. So with that small amount of data that was given before, and with this simple but very small code, we could predict this amount of data which has been predicted in future. And this is how, like, a simple AI and cloud modeling based weather forecasting cloud modeling based source is predicted. I would like to go back to my presentation and run from there. So these were the references taken. Google Cloud Tech, the video was from Google Cloud Tech, the code which has been shared by Google itself, and Google Earth Engineer. It is a very effective way. There is one more complex website which shows climate predictions and time lapses of climates. Because of lack of time, I cannot show it here, but if you guys want, you can check it out surely, because it shows climate patterns and time lapses of the last 37 years, and these help predict global warming overall throughout the planet. So this is a very interesting resource. So thank you everyone for your patience. I would like to thank Sir once again for giving us this opportunity to talk on this topic.